Good morning, guys. Today our topic is series resonance, and it's part two, that is Q factor, etc. Okay. So first of all, heading is Q factor of okay. So what is the Q factor? Actually, Q factor means it's storage factor sorry, of any inductor or capacitor. Means how much input voltage we provide and how much we get as an output from this inductor. This ratio is called Q factor. Say here is an inductor. Okay, so we are providing, say, V input. Okay, some voltage is providing. It must be AC, it must be AC circuit, and we get as an output, if we give some voltmeter, then we get, say, V output. Then Q factor is called the output voltage, or the output voltage, or the sorry, this is not O, this is V. This is the output voltage or voltage across this inductor divided by input voltage or the applied voltage, input voltage. So this is called the Q factor. Same things is applied for the capacitor. Say if you provide some input voltage, there must be some resistance or any other circuit. But if you want to measure the Q factor of this capacitor, this is the capacitor, then you have to apply the voltmeter. Okay, this voltmeter will give you the voltage across this capacitor. If this is the AC, say this is input voltage, then Q factor of this capacitor is just the output voltage or the voltage across this C divided by the input voltage. This is called the Q factor, or sometimes it is called quality factor, or sometimes it is called a storage factor. Means how much voltage it will store. Say if you provide 5 volt, it may be 5.5 volt or something. So you can see this is the some amplified voltage is there. This is called the Q factor. So 5.5 divided by 5, what will give you? 1.1. This is the Q factor of this C. This is called the Q factor or the quality factor, or sometimes it is called the storage factor. Okay, so let's go for the definition. Okay, we are going to here. In a series resonating circuit, Q factor, or you can say the quality factor, is defined as the ratio of the voltage across or capacitor to the applied voltage. So we can write Q of L equal to VL, voltage across the particular inductor, and input voltage, or Q of C is the voltage across the capacitor, or, and as per the input voltage, B in or the input applied voltage. This is called applied voltage, and this is called voltage across the capacitor, voltage across the capacitor. Same things is, that is, voltage across the inductor, and this is applied voltage. Okay, or the input voltage, whatever may be. So this is a quality factor. So you can see always in this series resonating circuit, if you applied some voltage, you get some greater voltage than this applied voltage for the inductor and as well as for the capacitor. So these things is just like a amplification or the magnification. Okay, magnification. So it is also the voltage magnification in the circuit. At resonance. Guys, what is the magnification and what is the amplification? Amplification means if input is, say input is 2, it uh, it is amplification. It may be 2.3, it may be 2.4, whatever may be, but no particular multiplication is there. This 2.3, 2.4, 2.5, whatever may be. But magnification means it's it must have some multiplying factor, means some particular ratio, say 2 into 1, that is 2, 2 into 3, that sorry, 2 into 2, that is 4. So this 2 times 1 time 3 time multiplication, so this is called the magnification. It must have some certain in constant, or say 1.1, then what happened, 2 will give you 2.2, say 2.2, then it will be 4.4. So it has some regular shape, that is the a particular multiplying factor, then it is called the magnification. So in this case, it somehow the some factor is there which will multiply this thing. This is called the quality factor. Okay, because look, this is a regular number, certain number. Okay, for this capacitor always it will be maintained. Say for this capacitor, this type of capacitor is there, its uh, quality factor is 0.1, or sometimes it is 1.1. So if you input voltage is, this is input voltage, this is quality factor, and this is voltage across this. If you apply this 2 volt, then it will get 2.2. If you apply this 3 volt, then it will get 3.3. If you apply this 4, then it will get 4.4. So this is called the quality factor. So it is Q into Vc by V input. So V input equal to Vc. So this is called a magnifying factor, or this is called a quality factor. Now we can write this for the inductor, Q equal to VL by V for inductor. Okay, and this is Q for Vc by V for capacitor. So we can also write this is the current at the initial condition I0 XL and IR. Okay, this is the formula of VL, this is the formula of normal V into R. Okay, so I and I will just cut around and we get XL by R. We can write XL equal to omega not 0 by R. Okay, so in this case we can also write I naught by XC. This is I naught R. So this will be cut off and we get XC R. We can write XC means 1 by omega naught C into R. So it will give you omega naught C into R. Okay. So this is the equation. Again, we can write this another way. VL equal to I naught XL equal to V by R into XL equal to V by R. This term, it will be giving you this omega naught L, this term. Okay. So what we can write? We have seen Q equal to XL XL by R. Okay. So we can write just keeping here omega naught L by R and this V will be just this. So you can see this things is Q. So we can write this Q into V. Just I have write before. Same way we can write in this case we know that is VC is initial current or the total current by XC. Okay, so we can write V by R this into XC. We can write XC means 1 by omega C V by R, or we can write in this way V 1 by R dot 1 by omega naught C. So if you multiply this, then it became V into 1 R omega naught C. You can see this item and this item is same. So we can write that is QC into V. This is equal to this. So we can write this way. Another way, we can represent that is we know Q equal to omega naught L by R just before. So we can write this omega naught is root under LC. This is L by R. Okay, or we can write this. If we come take this, so what happens? This L means root L into root L. So I can divide it root L into root L. Here it is root L into root C into 1 by R. So 1 root cut down. So it became root L under root C, and this is 1 by R. So in this way, we can also represent the quality. If there is a circuit where we can get some capacitor, inductor, both. Same way for the capacitor, capacitance, Q equal to 1 by omega naught RC equal to 1 by omega is 1 by root LC for capacitor. Okay, and this RC is just remain same. So it's became 1 by R. Look, this C just like this. C we can write root C into root C. So it's became root C divided by, sorry, yes, root C. This is under 1. Okay, sorry, because this time is under 1. I'm doing it in the lowercase. 1 by R into root C divided by L and C. So this LC means another root into L, root into C. So just cut down, we get 1 by R by root C, sorry, root L into root C. Okay. So what happens? It will, this L became here. So 1 root L by root C and into 1 by R, or you can get 1 by R into root LC. Okay. This is the representation of quality factor. So next topic is bandwidth of series resonating circuit and its relation with this Q factor. The frequency band within limit of lower and upper power half power frequency is called switching circuit. Look, we are whenever one frequency is there, then we can say this is the something hertz is there. But whenever within this range, if so many frequencies, so many signals are there, we are taking only the bandwidth. Okay, bandwidth. And say for your FM band, we are taking some for one frequency, but for your data band, you can say this is some GB, some dB. Okay, so this is the bandwidth. Means within a range, within a frequency limit, there is so many signals are there. So many signals are there. Okay, in your bandwidth, in your mobile, you are applying some simultaneously. You are sending and receiving both data frequency, audio frequency, all frequencies are there. So this is called a band. Means in within this limit, some signal, some frequency of the signal which are not same. This is the difference are passing. So this is called the band. And what is the band structure? So say this is, if you get some band, this is 90 hertz, this is 180 hertz, etc. So say my band is that 90 to 180. We are taking this band. Within this band, within this band, our signals or information is there, and in this band we are just cut out. So this is called the lower frequency, and this is called the higher frequency of this band. Okay, within this limit, we are getting some information, and other signals are also coming. We are just take it as a noise, and we just cut out. So you can see the band has the in this band. This is the plane surface, straight line, and whenever this lower frequency is there, then it is coming lower zero to the some range, and again whenever the higher frequency is coming, it is again going to the zero. So this frequency is called a cutoff frequency. Oh, this is called the lower cutoff frequency, and this is called the higher cutoff frequency. Okay, so within this limit, within this frequency limit, we are with this frequency are acceptable, and this is carrying the information. That's why this is called the band. This bandwidth are acceptable. So the higher cutoff frequency minus lower cutoff frequency, it is one band. Okay, in your DSP or digital signal process, then you can see, and there is some filter for electrical network also, which filter will give you the concept of band, and when it will filter, the unwanted signal will be filtered out. This portion will be filtered out. Okay, so there is a some filter is there. Down, they say LPF. Okay, this is low pass filter, means lower side frequency is there. Say this is your 90 hertz, this is 180 hertz, this is 270 hertz. You are taking 90 to 270, so filter will cut down this portion. So this band is acceptable, and this filter is called LPF. low pass filter. Okay, if your frequency is just like 90, 180 and 270, you are taking only this high frequency range and this is cut down, then this filter is called high pass filter. High pass filter, because this range 180 to 270 and the higher range will be acceptable, but so this is the called high pass filter. And some filter is there is band pass filter for this particular range. Say this is 100 hertz and this is 300 hertz. Within this limit you are taking this part and delete this part. So this filter is called band pass filter, BPF. Okay, in this way there you can take more information regarding this band. But what is the relation between bandwidth, and this portion is called bandwidth? Okay, so bandwidth and the quality factor. So this is the band, and the response of the resonating to be flat. Okay, and what is the relation? This q equal to omega naught by omega 2 minus omega 1, or if this is this is f1 and this is f2, or this is lower frequency, this is higher frequency. Okay, so we can write this is, and this is f2 means upper cut and this is lower cut, and this is called, this portion is bandwidth. And what is this? This is called resonating frequency. This is called resonating frequency. Okay, this is the
Sir, we
thing.
have empty class from 9:50.
Okay, okay. Tanmay sir will take this.
Yes, sir.
Okay. Okay, you can leave it
Sir, what is the syllabus for your internal?
for today up to this.
Thank you, sir.
Okay. So the selectivity of a resonating circuit is defined by the ratio of resonating frequency to the bandwidth of the circuit. This is the resonating frequency and this is the bandwidth. This is the bandwidth. This is also given as the Q. Selectivity of a resonating circuit is defined by the ratio of F0 to the band of the circuit. Okay. And F1 and F2 are also called 3 dB points as the current ratio I1 I0. So what is the dB? What is the dB? This is 20 log 10 base I1 by I0, or we can say this is 20 log 10 base 1 by root 2. Okay, so dB is the -3. So we can say that, so I1 is lower than I0 by 3 dB, and similarly if one is also lower than F0 by 3 dB. Now the power dissipation. Would be half of that this is at. Okay, so Look, this is the larger R. This is the smaller R. Okay. If the small r is there, r is the damping factor, then this your circuit or system will be oscillating. So small r. If this is a larger r, then your system will be damped and it will reach under damped condition. Reach this stability at the under damped condition. So guys, up to this, I'm going to stop here. Thank you.